This is the recording for the Unit 2 practice test. Newton's laws. There are three of them: inertia, F equals ma, and the action-reaction principle. So let's see. Question 1. Roll a rock at the end of a string on an ice-covered pond and it follows a circular path. If the string breaks, the tendency of the rock is to follow a straight line path. It just continues in the motion that it was at, which is tangential to the circle it was making around you before the string broke, and then it just slides across in a straight line. Inertia. If no external forces are acting on a moving object, it will continue moving at the same velocity. That is inertia. The second one here is correct as well, but it also doesn't change direction. So an acceleration does two things: it speeds up or slows down, or it changes direction. So if there is no acceleration, which there isn't if there are no external forces, then the object will just move with the same velocity, same speed in the same direction. Magnitude of the gain on speed each second for a freely falling object is about 10 meters per second. Notice that this says magnitude, which means even if it's a negative number, you just call it 10 in this case. Yes, it is increasing with negative 10, but it says magnitude. That's what that word means. Of course, the more exact number is 9.8 or negative 9.8. By the way, when G itself is 9.8 and in our textbook as it's rounded is 10, when you plug it into an equation, you're not just plugging in G equals 9.8 or G equals 10, you always will plug in a negative G. So negative 10 or negative 9.8. Again, this particular question calls out the magnitude of that. Strange as it may seem, it's just as hard to accelerate a car on a level surface on the moon as it is here on Earth. This is because the mass of the car is independent of gravity. You would have to picture that particular vehicle on the moon, it has less weight, 1/6 of what it has on Earth, because the moon's gravity, surface gravity, is less than what it is on Earth, which also means that the support force is only 1/6, because that's all that the moon needs to provide. I mean, the moon's surface needs to provide. And that also means that the traction as well as the friction on the car is also just 1/6. So with the traction being 1/6, it's actually accelerating less than what it could on the Earth. But then again, there is also less friction going on, so overall the acceleration actually comes out to be virtually the same for the car. Okay. By the way, for this one here, if you Google this particular question, look at physics.stackexchange, and you will find a number of interesting answers that pretty much all boil down to, yes, that statement is actually true. And then, of course, it's hard to compare because you would actually have to compare the moon car that was driving around. And, of course, the surface that you have on the moon is different than anything that you find here on Earth. I mean, you would have to resemble the same kind of surface that you actually encounter on the moon to really make an assessment of that. All right, an object is propelled along a straight line, An object is propelled along a straight line path by a force. If the net force were doubled, the object's acceleration would be twice as much. So twice the net force means twice the acceleration for the same mass object, and that is F equals ma, Newton's second law. Notice that this practice test here kind of progresses. We're starting with Newton's first law, inertia, and then we're going to go over to Newton's second law about acceleration, and then towards the end will be Newton's third law. All right, compute the answers and match the following. An object is pulled northward by a force of 10 newtons and southward 15 newtons. So subtract 15 from 10, which is negative 5, but again it says magnitude right here, so the net force therefore is 5 newtons. Falling object of weight 10 newtons encounters 4 newtons of air resistance. So 10 minus 4 is 6 newtons. So it's this answer here. And again, it's downward. So there is 4 newtons of air resistance. So it's technically a negative 6, but it says magnitude right here again. Falling object of weight 10 newtons encounters 10 newtons of air resistance. The net force on the object is 0 newtons right there. By the way, a falling object that encounters more air resistance than its weight, that doesn't mean it's going to go up. What happens to it is that it's slowing down. So imagine a skydiver who has reached terminal velocity while he or she is balled up, but then suddenly he spreads his entire body out. Well, that means more air resistance is there, and that will actually slow him or her down with an upward acceleration. Acceleration does not mean the direction of motion. What it means is how the motion changes. The velocity, that is the direction of motion. Okay, last one here. A bag of groceries has a mass of 10 kilograms and a weight of about negative 100 newtons. So here, because the weight is down, that's where I attach the negative, and I'm trying to be consistent throughout the entire class, always attaching that negative here. If you come across something where you don't see that particular one, please let me know and I will try to fix it. Also, as you have the weight here as negative 100 newtons, as you divide by 9.8 or the rounded 10, you come up with the mass of 10 kilograms. So the weight equals mass times negative gravity. So whenever you see a mass, you will know its weight right away, or whenever you see the weight, you will know its mass right away. Granted, if you're relatively close to the surface of the Earth. Even if you're in an airplane, that is still considered relatively close to the Earth, because you would have to compare your distance to the entire radius of the Earth, which is huge, 4,000 miles. So in any case, 10 kilograms, negative 100 newtons. And again, the negative is there because we need it for the calculations. All right, and that's what the next one does right here. So an object with a mass, and here it is, weight equals mass times negative gravity. The G being itself a positive 9.8 or a positive 10. When you plug it into the equation, you always plug it in negative G. So an object with a mass of 28 kilograms has a weight of about, well, negative 200 newtons. And then it's just slightly off the screen. It says, more accurately, it's negative 270 newtons because you would be multiplying with 9.8 more accurately. And then 54 kilograms, well, the quick way of doing it is negative 540 newtons. If you do it a little bit more accurately, you get this number. And 779 kilograms, right away you know that the weight is negative 790 newtons because of the really convenient negative 10. Do it a little bit more accurately with the more accurate negative 9.8 and you come up with negative 770. All right. Hang from a pair of gym rings, but not necessarily symmetrically, and the upward support forces of the rings will always add up to equal your weight. So if your weight of 150 pounds is pulling down, you need a force of 150 pounds pushing or pulling you up in order to make up for that, because otherwise you'd be accelerating downward or upward. And so here it says, hang from a pair of gym rings. You're just hanging there. And yes, they add up to your weight. They don't split them up evenly, 75, unless you're hanging there symmetrically, but it says in this problem here, not necessarily symmetrically. So you could, for example, push yourself over a little bit to one ring, and that then supports more weight than the other one. In this case, that support force would be, I guess from the ring itself, it's a support force. From the rope, of course, it would be a tensional force. Truck exerts a force of 3,200 newtons on the car, accelerating it at 2 meters per second squared. So force equals mass times acceleration, or in this case, it is mass equals force divided by acceleration. So 3,200 divided by 2 is 1,600 kilograms. The rocket becomes progressively easier to accelerate as it travels upward from the ground, mainly because the mass of the rocket decreases as fuel is burned. Somebody could say, well, it's going away from Earth, so gravity is getting less. Well, that's true, but as it's going through the atmosphere and then just as it's getting into outer space, it's really not that much further. Again, the radius of the Earth is 4,000 miles, while when you're just in outer space, you're another 200 miles up. yeah, you know, that is 5%, and in that case, 10%. Actually, gravity is about 10. Let's see, is it 5%? Yeah, 10% less. So it is appreciably smaller, 8.8, but it really is the mass of the rocket. You know, the staged rocket that's just, and there's a lot of fuel in there. I mean, the fuel to payload ratio is huge. And so as you dump that, the mass is getting much smaller, and therefore it is this answer here. It says in the problem, it is mainly because gravity does become weaker with an increased distance, but you would have to go quite a distance away to become really as effective, or yeah, as effective as the mass loss is. Which has zero acceleration. An object, mechanical equilibrium, that's what it means. Mechanical equilibrium means that the net force is zero, in which case there's zero acceleration. Moving at constant velocity, that is also the definition of constant velocity. There is no acceleration acting on it. At rest and staying at rest. So if you're at rest at a traffic light that just turns from red to green and you're accelerating, well, that means you're no longer staying at rest and you are accelerating. But this one here specifically says at rest and staying at rest. So these three answers. In free fall, well, in free fall, where we, so to say, neglect air resistance, you are accelerating at negative 9.8, rounded negative 10. When you're changing the direction of motion, well, you need a net force to act on the object, a car, for example, in order to get into a turn, and that net force then produces a centripetal acceleration which gets you into that turn. Hence, this one doesn't apply here because it says zero acceleration. You have to stay in constant motion and be in mechanical equilibrium. If an object of constant mass experiences a constant net force, it will have a constant acceleration. So divide a constant net force by a constant mass, you come up with a constant number, which is the acceleration. Force divided by mass is acceleration. Accelerations, let's see. Compute the answers and match the following. A rock is thrown vertically into the air at the top of its path. Its downward acceleration is negative 9.8 meters per second squared. Nothing to calculate in this case. It's a given. A jumbo jet has a mass of 100,000 kilograms. By accelerating on the runway, the thrust for each of its four engines is about 50,000 newtons each. I guess. Oh, it says each right here. So 4 times 50,000 is 200,000. Divide by 100,000 kilograms, you come up with 2 meters per second squared right there. Skydiver with a mass of about 100 kilograms experiences air resistance of about 700 newtons and a downward acceleration of about, the answer that I checked here is 3 meters per second squared. Why? Well, again, when you have the mass given, you always have the weight given right away, which is about negative 1,000 newtons. Why exactly? It's negative 980. But let's just go with the negative 1,000 for time being. This time around, the skydiver obviously does encounter air resistance. Once in a while we do talk about free fall, but that has certain reasons because we quite often choose free fall because the equation itself for air resistance is quite complicated. But if we have both numbers given here, we just subtract them. So in this case, the skydiver does encounter air resistance 700 newtons, negative 1,000 down, 700 up, subtract the 2, which is negative 300. And then the downward acceleration is negative 3 meters per second squared. So maybe I should throw the negative in here, or I should put a downward there in the back. I'll try to fix that when I'm done with this recording. Make a note. All right, let's see. Oh, I didn't have this one yet. It's a sack of potatoes weighing about negative 200 newtons, which means 20 kilograms, falls from an airplane. As the velocity of fall increases, air resistance also increases. When air resistance equals about 200 newtons, at which point the two forces, the weight and the air resistance, are the same. That means that the net force is zero, so the acceleration is 0 meters per second squared. That's why that's the right answer. Again, acceleration does not mean the direction of motion. It means how the motion is changing. So 0 meters per second squared simply means that at this point, the motion is not changing, and we already know that the sack of potatoes is falling, which means it continues to fall at that particular velocity that it's falling down. Apparently it's its terminal velocity. Okay, an object released from rest on Mars requires a time of 1 second to fall a distance of -2 meters, which is 6.5 feet. What is the acceleration due to gravity on Mars? Well, actually you need an equation, and I give it to you here, so you need to figure this one out. Here, actually, I should take the negative out right here, so I also will fix that after class. I'm sorry, after this recording, question 14. Because there is already a negative right here once I plug it in. So I have then -2 meters divided by a negative. This is my unknown here. G star is the gravity of Mars, and then I plug in the 1 second that is given for the time, and then I do the calculation, and I come up with 4 meters per second squared. And so that one is the right answer. Again, G, the acceleration due to gravity, is a positive number. Once I plug it into an equation, it actually it has a negative added to it in the front. And the G star here simply means the acceleration due to gravity on Mars' surface, which is different from Earth, as any kind of surface gravity of a planet or a moon or a star or what have you depends on the mass and the radius of that particular object. The -10 or -9.8 for us, of course, is important because many of the problems that I'm throwing at you here in this physics class are, of course, near the surface of the Earth. Okay. Yeah, looks like action-reaction principle. Whenever there is an action force exerted by object X on object Y, there must be a reaction force exerted by object Y on object X, which is exactly equal in magnitude and in the opposite direction. Player catches a ball. Consider the action force to be the impact of the ball against the player's glove. The reaction to this force is the force the glove exerts on the ball. This one here, of course, slows the ball down. This one here, the impact on the player's glove, the baseball player actually feels that. Yeah, there's an appreciable force pushing on that. That is why actually he is using actually a glove, because if he tried to, or she tried to catch it with their bare hand, that's going to be quite a sting. Also, there's another baseball problem in the next unit on momentum. There's a reason why the baseball player goes with the motion of the ball backwards, because it extends the time of catching it. Don't go forward with the glove trying to catch the ball. You will exert a tremendously larger force, and that really could perhaps even, I guess, injure your wrist due to the torque that it exerts on it. All right, let's see. A person is attracted toward the center of the Earth by -500 newtons. So apparently, wow, that's a really lightweight person, 50 kilograms. That's 110 pounds. Gravitational force downward. The Earth is attracted toward the person with a force of, well, 500 newtons upwards. That's the action-reaction principle. The Earth is attracted with the same force towards me as the Earth attracts me downward. Of course, the Earth cares less because its mass is so huge. In my case, well, in this person's case here, the weight of this person here is apparently, the mass of this person is 50 kilograms. So if they were stepping off some stairs or a table or something like that, they would accelerate downward at -10 meters per second squared. And so they feel a tremendous or quite a bit of acceleration. It's very slight elliptical orbit. Earth is closest to the Sun in early January. Hence, it moves closer in the months before January because the gravity is larger as it's a little closer. Since the difference in distance does not determine the seasons, it must be the tilt of the axis. So it's just put parentheses that I put ahead here. So during December, when the Earth is moving closer to the Sun, that's when in early January is actually when we're closest to the Sun. Again, it's the tilt of the axis that determines the seasons, not the distance. Then the Sun moves toward the Earth by a smaller distance. Again, it's the action-reaction principle. The Earth is attracted more towards the Sun in December because it is closer, and therefore the Sun also moves toward the Earth a little bit faster because of small distance. Again, the Sun probably doesn't care because it has so much more mass. All right, Arnold and Susie Small each pull very hard on opposite ends of a rope in a tug of war. The greater force is exerted by both the same, interestingly enough, because it's the action-reaction. Now, we pretty much figured that Arnold will win this, and that's why I have a follow-up question here. Although Arnold and Susie in their tug of war pull each other with the same force as required by Newton's third law, answer to the last one, when that force is applied to each one of them, it makes a bigger difference, produces a large acceleration to Susie because of her having less mass. This is explained by Newton's second law. I pretty much outline this here. I talk about acceleration, I talk about force, just slightly off the screen here, there it is, and that then of course force divided by acceleration, well, that's the mass, that's Susie's mass, there it is, or force equals mass times acceleration. All right. When the net force on an object equals 0, then the velocity is constant, the acceleration is 0. The velocity could be a constant 0. Again, zero acceleration does not mean no motion. What it means is the motion isn't changing. So it could be that the velocity already is 0, the object is at rest, and then it remains to be 0. But it could also mean that the velocity is 50 miles an hour and then it remains at 50 miles per hour. Again, zero acceleration means no change in motion. Let's see, and I believe this is actually the last one here. Check all of the following that are considered forces. A force is measured in newtons or pounds. You should look through the index in the textbook and find force in various chapters, and then see also various websites. And I just checked the first one here, gravitational force, but if you read carefully through these here, I believe all of these apply. And they all take on a capital F for force, and then I just put a little index here that means something else. So buoyant force here, normal force or support force here, magnetic force for some reason also takes a B. The electric force, because of the word Coulomb, takes Coulomb for charge takes a capital C there. Lift on a wing, FL, and so on. These are all forces. The computation problems, those are in a different recording, and those are also in the posted worked out problems in physics. And there was the recording for the Unit 2 practice test on Newton's laws.